Now we've looked at the atmosphere, the biosphere, and so on and so forth. Now we're going to look at the Earth system from the perspective of cycles. We're going to start by looking at the water cycle because it's familiar and relatively straightforward. And after that, we're going to look at the carbon cycle, which is a lot more complicated. So let's begin with the typical water cycle diagram. This is just one of millions that are on the internet. I don't think there's one in the book. But the basic idea here is if you can have some water at any given time, might be in the ocean in the liquid form, also some of it might be ice. Eventually that water will evaporate and go into the atmosphere as vapor. Some of that vapor will condense to form clouds and maybe rain over the oceans. Other vapor may condense to form clouds. Not every cloud rains, of course, but those clouds may rain and snow over the land. Eventually that ice would melt, or the rainwater would run down the surface of the land into the rivers and back out again. So basically that's the water cycle. And because we're scientists, we want to do something a little bit more than just talk about the cycle itself. We want to talk about some details. And those are contained in figure 2.2. Those are contained in table 2.2 in the book. So table 2.2 shows us the masses of various reservoirs of water in the Earth system. The one we're most familiar with maybe is the atmosphere. That's certainly one we're going to be interested in. And it turns out that there's only a very tiny amount of water in the atmosphere, 0.01 times 10 to the 3 kilograms per square meter. Residence time is an estimate of how long the water vapor stays in the atmosphere, and you can calculate that from observations of evaporation into the atmosphere and precipitation out of the atmosphere. And it looks as though the residence time in the atmosphere is on the order of days. If we want to look for where all the water is, you have to look in the crust and mantle of the planet. 20,000 units of water are locked up in the crust and mantle, and it's locked up there for a long time, 10 to the 11th year. So basically it's lost to us, definitely from a day-to-day basis. That's not to say that there isn't water underground. That's a different pool of water, as it were. 15 units are locked up underground in things like aquifers, and those are locked away for maybe hundreds of years. And that doesn't include the fresh water that's in lakes and reservoirs, 0.6 units. So most of the water is locked up in the crust and mantle. Quite a lot is also locked up in the oceans, 2,700 units. And a surprisingly large amount of water is locked away in the Antarctic ice sheet, 53 times 10 to the 3rd kilograms per square meter. And the residence time is estimated there at 100,000 years, depending upon the ice age cycles. So on the order of 100,000 years, Antarctic ice is locked away. Greenland ice, quite a large amount, 5 units locked away for on the order of 10,000 years. And finally, alpine glaciers, a much smaller amount. This is the kind of thing you find at Glacier National Park, 0.2 units. That's still, 20 times more than is in the atmosphere, and it's locked away for hundreds of years. So the take home is you should be familiar with the elements in this table, the names of the reservoirs, a rough idea of how much mass is in each reservoir, and what the residence times are. Okay, so summarizing in one slide, what do we have? We have a huge amount of water in the mantle. The only way it gets out is via volcanic eruptions. Eruptions brings carbon dioxide into the atmosphere, water vapor, and some other gases. But of course those are few and far between these days. Large amount of water is in the oceans. A considerable amount of water is in the ice sheets, Greenland and Antarctica, and only a teeny amount, that's a very scientific term, very teeny amount is in the atmosphere, and it doesn't stay there very long, a short residence time. Now, thinking about the hydrological cycle, especially over the land, but also over the ocean, there's two things we want to always keep in mind. One is precipitation, and we use this symbol P to denote precipitation. Whoops, didn't want to do that. So the symbol P denotes precipitation. And then the other is evaporation, and we use the symbol E for evaporation. Whoops, didn't want to do that either. Let's have a look at figure 125 in the book. This is a map of global precipitation. We saw this earlier in the semester. Always you want to look at these kind of bands underneath the color bar to see what's going on. So the redder areas, bluer areas are more precipitation, and the yellower areas are less precipitation. So we know roughly around the planet where it rains. It rains a lot around the middle of the planet, across the middle of the Indian Ocean, the Western Pacific, the Central Pacific, and the Central Atlantic. Alright, so that's precipitation. The other thing that we're interested in is evaporation. Precipitation is easier to measure. You can just set out tin cans all over the place and measure precip. Evap is more difficult to measure, but the important thing to think about is that over the globe, the two should be roughly equal. Why isn't that working? Pen. Over the globe, the two should be roughly equal. Oh, that's interesting. Evaporation over the long term should equal precipitation, and we write that this way, and the overbar here is a way that we use often to denote some kind of an average. So the average evaporation equals average precipitation. This is not true at any given location, and it isn't necessarily true for a particular time. So this is an average over, say, a year or a decade, and maybe over an entire area such as all of North America. You can easily imagine, for example, that over the Sahara Desert, evaporation exceeds precipitation. And along the intertropical convergence zone, precipitation exceeds evaporation. Here's a way to visualize what precipitation and evaporation are doing in the atmosphere for just a single column of air. Alright, so here's my column of air. The ground is down here. And within the column, which probably goes to the top of the atmosphere, you've got precipitation going on, falling on the ground, and at the ground you've got evaporation going on. Precipitation can actually be quite complicated. You can have a cloud that's precipitating. Some of that liquid or ice will evaporate or sublimate on the way down. Not all of it makes it to the ground. But anyway, we have the general idea of precipitation and evaporation. There's one other factor, and that is the transport horizontally into and out of the column of water vapor by the prevailing winds. So we need to factor that in as well. In fact, there's another factor which I don't think is mentioned in the book, but we can talk about that really quickly. If I can just get the pen to respond, thank you. And that is that typically when it rains, you can have some runoff at the surface. Come on, catch up with me. That's supposed to be the word runoff. Anyway, you can have precipitation onto the surface, run off on the surface or maybe into the ground, and evaporation again. If we take this approach and look at the land, then our column is now below the surface. So you have precipitation from the air onto the land, evaporation out of this column back into the air, and transportation out of it. And people study this. This is a part of the study of hydrology to try to get an idea for how much water is being put into aquifers and things like that underground, and maybe to get a sense for how much flooding to expect.